Okay, so in the interest of time, let's get started. Welcome everyone to the APS Climate Physics Seminar. It is my great pleasure to introduce Professor Alex Robel. Alex is a professor in Earth and Atmospheric Science in Georgia Tech, where he leads the Ice and Climate Group. He received his bachelor degree from Duke University in both physics and earth sciences, and then a PhD from Harvard in Earth and Planetary Sciences. He was a recipient of the NOAA Climate and Global Change Postdoctoral Fellowship. In my perspective, what distinguished Alex's work from that of many others is his introduction of new and innovative ways to model cryosphere problems. Alex has pioneered the use of statistical mechanics and dynamical system theories to study cryosphere. His approach ranges from elegant conceptual models to ice sheet scale simulations, from deterministic to stochastic. Today, he will tell us about what physics can tell us about ice sheets and future sea level rise. Without further ado, Alex, please take it away.
Great. Thanks, Yao. And thank you for the invitation to speak at this virtual seminar. It's maybe somewhat fitting that after a while in science, I've sort of come full circle back around to physics. I started out as a physics major and determined to be a physicist as an undergrad, and got a scholarship from APS when I was an undergrad to continue on in physics. Ultimately, I guess sidetracked by working on interesting problems in climate, but I think as you'll see today, I never strayed too far from physics. It's really always been at the heart of a lot of how I like to think about problems in climate science. As Yao said, I'm currently an assistant professor at Georgia Tech. And the work that I'll be talking about today, I'll be talking about sort of a few different problems that I and my group have worked on, and also collaborators. And where necessary or possible, I will try to give as much credit to all the fantastic students and collaborators who've really made all this work possible. So ultimately, why are we trying to answer these questions? And it's sort of one of the answers is sea level rise. So we know with a high degree of certainty that sea level has been rising globally, or near globally, due to expansion of the ocean. When seawater is warmed, is heated up, it takes up more space. And then also adding more mass of water to the ocean through glacier and ice sheet melt. And so the big question, within our field is how much more of this should we be planning for in the future? And so this picture kind of illustrates, the sort of present reality of this problem. This is from my hometown of Miami, Florida, where this is kind of a typical high tide day. This is a regular occurrence in Miami. And actually now it's really a regular occurrence in coastal communities, all along the east coast of the United States, and particularly here in the Southeast and in the Gulf Coast, where sea level has been rising locally at about twice the global mean rate. So sea level rise is a serious problem, and understanding how much more we should plan for is a particularly important question because there's hundreds of billions, if not trillions of dollars that are going to be invested in the coming decades into protections against sea level rise in coastal communities. So here is just one example of a proposed storm surge barrier in Miami, the different colors showing different segments of the proposed flood walls that the Army Corps of Engineers has proposed to build. And of course, the question is, the key question in any debate over this is, where should you be building these and how high should they be built? And ultimately, this question of how high they should be built, really comes down to how well can we predict future sea level rise. And so here is sort of our current consensus best estimate. This is from the IPCC's special report on changing oceans and cryosphere from 2019. And the big plot on the bottom shows the kind of consensus estimate for what we think global mean sea level will do over the next few centuries. due to either a high emissions scenario in red or a low emissions scenario in blue. And so this is a great plot for really showing that the cryosphere is sort of a can be thought of as a slow moving system, in that it the difference between high emissions and low emissions scenarios really only starts to emerge at the end of the 21st century. And so seeing the difference between these possible future trajectories of how much carbon we're putting into the atmosphere takes a while to unfold, but once it does start unfolding, it progresses, very quickly. So we're talking about, potentially several meters or, 10 or more feet of sea level rise, over the next few centuries. And, for large areas of the world, this would be, simply an existential question of whether those states in the case of Florida, or countries in the case of Bangladesh, or many countries in the South Pacific, small island countries, whether they can even continue to exist. So answering these questions is important. And really 2100 is an important turning point, both because that's when high and low emissions trajectories start to diverge, but also because that's when the increase in uncertainty, which is denoted by the shading bars on this plot, when the increase in uncertainty starts to really be amplified. So after 2100, the size of the uncertainty, the size of that shading, is close to the size of the whole signal itself. So there's several meters of uncertainty, or one or more meters of uncertainty, even at times when the sort of mean projection is close to a meter or a few meters. And so, understanding this uncertainty is really important, and that's what I'll be talking about in the first part of my talk today. And this is particularly relevant. This problem is particularly relevant to the physics community. In 2021, I'm sure folks on this call are very familiar with the recipients of the Nobel Prize in 2021, which included two climate scientists, Syukuro Manabe and Klaus Hasselmann. And in particular, Hasselmann is well known in the climate modeling community and the climate science community for his early work on stochastic climate models. And so here's just a citation from one paper where, our modern understanding of climate change and uncertainty in climate projections is really indebted to these ideas that Hasselmann, imported from statistical mechanics and physics. Now, those ideas up until a few years ago had largely not reached the field of glaciology and ice sheet modeling. And so the first part of my talk will be, what can we learn from statistical mechanics and statistical physics in order to understand more about uncertainty in sea level projections. So that'll be the first part of my talk, which is focused on stochastic perturbation theory and chaotic climate variability, and just largely about stochastic ice sheet modeling. Okay, so if you've heard anything about Antarctica in the news, and particularly Antarctica in the changing climate in the last 10 years, it probably has something to do with this idea that Antarctica might reach this threshold of no return, right? This point of no return, where basically once it loses a certain amount of ice, it will continue, even without further climate change, will continue to contribute to sea level rise in the future. And so a number of articles, some more sensational than others, have been written on this in the last 10, 20 years. And this idea largely comes from, very real sort of scientific concept within the glaciology community, having to do with marine ice sheets. So marine ice sheet is an ice sheet like large parts of Antarctica, where the bottom of the ice sheet is resting below sea level, or on sea floor, what would otherwise be sea floor. So what this map on the left shows is a map of Antarctica if you took all the ice off of it. And so areas in blue are below sea level, and areas in brown and green are above sea level. So what you can see here is that large parts of Antarctica, and particularly West Antarctica, which is on the left-hand side of this figure, are resting, 500, 1,000, even up to 2,000 meters below sea level. And that makes them susceptible to something that is popularly called in the ice sheet or glaciology community, the marine ice sheet instability. Many people have quibbled with that term. I'm not going to get into the sort of semantics of that, but I will explain what we mean by marine ice sheet instability here. So here's a cartoon of a glacier that comes into contact with the ocean. So this is kind of like a side-on view of a glacier. And so on the left-hand side, you have the grounded part of the glacier. That is where the ice is resting on the solid earth, which is drawn here schematically as a brown line. And then on the right-hand side, that glacier is extensive enough that it reaches the ocean, or at least it reaches a place where the solid earth is deep enough that the ice is thin enough to float on top of the ocean and basically lift off of the seafloor. And so this is what we would call something like a marine terminating glacier. That is a glacier that flows into the ocean and then is in contact with the seawater. Okay, so in this picture, the transition from grounded ice to floating ice, we call the grounding line. And so ice is flowing from the grounded ice to the floating ice. And then if the bed is bumpy, there can be parts of the bed where the bed, the solid earth, is getting deeper towards the interior of the ice sheet on the left in this cartoon. Okay, so this is the setup. And then if we think of sort of this glacier as a simple box model, we can think of mass gets added to the glacier through accumulation due to snow, which in Antarctica, largely speaking, although this is changing, at the surface of the ice sheet, ice is accumulating due to snow piling up on the ice sheet, compressing over time and turning into ice. There is not a ton of surface melting in the present day on the surface of the Antarctic ice sheet, but that ice flows under its own weight due to gravity downhill, and the loss of ice from the grounded part of the glacier is just due to the ice flow, or this grounding line flux that I have here in the schematic, through the grounding line. Okay, so if you can maybe remember your simple graphical stability analysis that you might have seen in a dynamical systems class or textbook, like the wonderful one by Stephen Strogatz, which is where I learned about this from. We can think of the flux of ice in, which is the blue line in this case due to snow accumulation, and the larger the ice sheet is, the more area it will encompass and the more snow it will accumulate, right? It'll have a larger area that catches snow accumulation. So basically, the longer or the further out the grounding line is, so on the x-axis here, we have potential positions of the grounding line. Sorry, I didn't write that here in this cartoon, but the x-axis is potential positions of the grounding line, same as in this top plot, in this top cartoon. And then the y-axis is the flux of ice into or out of the ice sheet. So the blue line is flux of ice in due to snow accumulation, which just increases linearly as the grounding line gets further out. And then the red line is the flux of ice through the grounding line. Now, there's been a lot of work done in our field about basically what determines the rate of ice flux through the grounding line, but by and large, you can think of the flux of ice as being proportional to some power of how deep the solid earth is below sea level at the grounding line. Okay, so a deeper or a thicker ice sheet at the grounding line will flux out more ice, and generally this actually goes to a pretty high power somewhere. Beta in this equation is somewhere between 3 and 5, or typically taken to be somewhere between, actually 3 and 6, I guess. Okay, so in a graphical stability analysis, we look at the places where these two lines cross, and those are the places where you can have a potential steady state, or what we would call fixed points, right? And then we can think of the stability of these fixed points by looking at the slopes of the various lines at these points. But I'm just going to quickly talk about a simple scenario where, due to climate change, the amount of snow accumulation on the surface of the ice sheet starts to decrease. So if P in this picture decreases, then the blue line moves down, the slope of the blue line moves down. And if we started at this black dot all the way to the right in this graph, then our grounding line would retreat a little bit. And you can probably see where this is going, which is that we can get to a situation where if the amount of accumulation rate decreases enough, the fixed point that was previously far out here on the continental shelf disappears, and the grounding line will want to retreat far inland. So this loss of stability of this fixed point is known canonically in the dynamical systems world as a saddle node bifurcation, right? It's basically you have a stable and an unstable fixed point, and they collide, and then they no longer exist past this bifurcation point. And so this saddle node bifurcation is, practically speaking, what is called the marine ice sheet instability, what all these news articles are talking about with West Antarctica. And that is because the reason why this bifurcation exists is because you have this reverse sloping part of the bed. That is this place where the bed gets deeper towards the interior of the ice sheet. And as I showed before, if I just back up for a second, there are many places in Antarctica where this is the case. And so this is the concern. So this is the setup for this problem. But what makes this problem trickier, the problem of predicting whether this sort of marine ice sheet instability might occur in Antarctica in the future, is that the climate system doesn't just smoothly change. Snow accumulation rate, melting from heat coming from the ocean. These things do not just smoothly change in a linear fashion, as in this cartoon that I just shown. The reality is that, the ocean and the atmosphere, being chaotic systems, are constantly fluctuating in terms of their temperature or, deposition of snowfall, these sorts of things. And so here are just two examples of ocean temperature at a glacier in Greenland, which has changed, varied quite a lot over the last 20 years, partly due to internal variability of the ocean system. And on the bottom, a proxy for ocean temperature at two large glaciers in West Antarctica, Pine Island and Thwaites Glacier. And so, what you can see is that there's just lots of internal variability in these factors, which are ultimately influencing the loss of ice from glaciers in Greenland and Antarctica. So how do we incorporate this variability into our understanding of, the potential for the marine ice sheet instability to occur in the future? So what I'm going to do here is I'm going to write down a simple model. So just going back to this cartoon for a second, we consider a simple model of marine ice sheet dynamics. The length of the glacier, that is the length from the interior of the glacier to the grounding line, is big L in this equation on the bottom. And then the P is the snow accumulation rate, and QG is the flux through the grounding line, right? So P is flux in, that's why it's positive. QG is flux out, that's why it's negative. And here we have a very simple, one ordinary differential equation model for the mass balance of a marine terminating glacier. Okay, so now we can add in this wrinkle of stochastic forcing, right? So if we this is a leap of logic that you'll have to take here, but if we say the chaotic variability of the ocean and the atmosphere cannot be predicted, we can emulate it, or we can approximate the distribution of potential ocean and atmospheric forcing on the ice sheet as a stochastic process. So here I've generically now rewritten this differential equation that I had on the previous slide in terms of a deterministic term. That's what you saw on the right-hand side in the previous equation, and then an added stochastic forcing term, which has an amplitude, sigma f, and then a random variable, which is drawn, or which is considered as a Wiener noise process. Okay. And so everything going forward from this slide is based on a paper that I wrote with colleagues Helene Cerruti at Dartmouth and Gerard Rowe at the University of Washington a few years ago. Okay. So this is going to be the most mathy, like 2 or 3 slides, but I'm just going to sort of go quickly through this idea. Basically, we use this mathematical approach called stochastic perturbation theory that was pioneered by Woo-Sok Moon and John Wetlau about a decade ago. And the idea here is that we can take a generic nonlinear stochastic differential equation and we can expand it about the purely deterministic, or rather, we can linearize the deterministic part of the model, right? So even if it's some very nonlinear, system, we can locally linearize it, and then we can expand that linearization in terms of the amplitude of the noise in the system. So that's what this first line does, and then we rewrite the solution in terms of, zero first and second order terms. And then the zero term is just the deterministic part of the model. And if we assume that the model starts at a steady state, we can actually ignore that. That's L naught in this equation. So that next first order term is really where the most important, the first and second order terms are where you can start to think about the different modes of uncertainty in the solution, right? So going from the first line to the last line, basically what we've done is we've taken our nonlinear SDE, we've linearized it, and what we've gotten to now is we've gotten to an approximation for that nonlinear SDE, which is actually the Langevin equation, right? So this is a linear model of where the variable is proportional to itself with some proportionality constant omega, and omega, whether omega is positive or negative, determines whether the system is stable or unstable, and then we have some noise forcing included here, right? The nice thing about turning this model into the Langevin equation is that the Langevin equation can be expressed or converted into the Fokker-Planck equation, which describes the evolution. Instead of thinking about stochastic trajectories of the system, we can now describe the evolution of the full probability distribution of the ice sheet state. So this is kind of where the ideas from statistical mechanics come in, where now instead of having a stochastic differential equation, we can actually think about the evolution of the full probability distribution. And the Fokker-Planck equation, which has been around for a very long time in physics, has known solutions for the leading order moments of the system, right? And so this is where it can become very useful to us, because now what we can do, and what we do in this paper, is we can have a theory for basically the spread of possible states of the ice sheet. That's the second moment of that distribution that we had on the last slide. And then also the skewness of that distribution, right? Whether it's skewed towards potentially more ice sheet mass or less ice sheet mass. And what we find is two things. Is that if you have a glacier which is going through this marine ice sheet instability, right? It transitions from being stable to being unstable, and it starts retreating rapidly as a response to that. The variance in possible states of the system in response to chaotic climate variability, it increases exponentially as the system is retreating in this unstable mode. Right? What that is to say, as your system becomes unstable, the spread of uncertainty increases very quickly in that system. Not only that, the other thing that we found in this paper was that the rate at which it increases also depends on the time scale of variability that you force the system with. So if the climate variability has lower frequencies or is dominated by lower frequencies, then the spread of uncertainty in the system is larger in that case. The other one of the other outcomes from this theory, or that things that we found from this theory, is that in these ensembles of projections of future ice sheet change, you will consistently always be skewed towards worst case scenarios. That is to say, more sea level rise. And this is simply a function of the nonlinearity inherent in these ice sheet dynamics. So that beta term, which we saw a number of slides ago, which sort of summarizes the nonlinearity associated with ice sheet flow and how it influences grounding line flux. That nonlinearity ultimately leads to this finding that you will systematically have skewed projections or distributions of projections where you have more higher probability of worst case scenarios or outcomes of higher sea level rise. And actually, you can look in more realistic. So obviously, this was a very simple mathematical model, but you can look in realistic projection ensembles for future ice sheet change. So here's two. I took two, but there's many other studies that show similar things of ensembles of simulations of Antarctica's future change. And what you can see in both cases is that as you go into the future and more glaciers in Antarctica become unstable due to this marine ice sheet instability, the uncertainty in the projections increases quite a lot, and it also becomes skewed towards higher sea level contributions from Antarctica. So this is something that we see in real projections as well. And this is important because the cost to adapt to future sea level rise or to prepare for future potential sea level rise increases with the long tail of uncertainty, not with the mean of uncertainty. That is, if you are in a coastal community and you're a planner and you're trying to, build infrastructure or a power plant or something like that, you're generally going to build so that there's a low probability of inundation, particularly if the infrastructure is critical or it's risky, in the case of a power plant or something like that. Or that rather there's a very bad outcome if it gets inundated. And so understanding and quantifying these long tails of uncertainty turns out to be quite important to how much money is spent and how much infrastructure or how much protection is built against future sea level rise. Okay, so far I've talked about this in the context of obviously very simple mathematical model. That was that paper came out in 2019. Since then, we have gotten 2 grants, one from the Heising-Simons Foundation and one from NSF, to sort of undertake parallel projects towards the broader goal of developing large-scale stochastic ice sheet models. And so that is to say a large-scale realistic model for how ice sheets will change in the future, including stochastic parameterizations for various processes in the climate system and in the ice sheet system. So in these particular projects, that is focused on surface mass balance, that is snow accumulation at the surface of the ice sheet, snow accumulation and melting at the surface of the ice sheet, ocean melting at the ocean interfaces of the ice sheet, and then fracture and calving of icebergs from the edge of the ice sheet. And so we've been working diligently on this over the last few years. So we've had papers out now from our wonderful cast of team members on this project. And so I'll just call out Vincent Verjean, a former postdoc, basically rewrote a large scale or part of a large scale ice sheet model in order to internally generate stochastic variability within the model so that you do not have to externally, provide the stochastic forcing to the model. All you've got to do is tell the model the statistics of the variability, and then the model internally generates the stochastic forcing within it. And then we've used a combination of observations and high fidelity models to develop stochastic parameterizations of snow accumulation and melting at the surface. That's a paper led by Liz Alty that's just coming out now in GMD. And then also parameterizations for ocean melting in a Greenland-like setting, paper by Vincent Verjean from last year, and in a more Antarctic-like setting, so a paper by student Shiva Muruganandam in SIZE in 2023. And then we have future work that's coming out in the next year or two, looking at sort of similar stochastic parameterizations for iceberg calving, and then the first large stochastic ensemble for Greenland, which we have currently run most of the simulations, and we're starting to work on the paper now. So that should also be coming out in the next year or two. So yes, we basically taken this, the mathematical theory is what we had before, and we've operationalized this and put it into a real ice sheet model, and the fruits of that are really just starting to come up now. I'm just going to highlight 2 interesting results that came out of this. So this is work. So one outstanding question within our field is how much of recent ice sheet mass loss is due to human-caused climate change. And many people are surprised to hear that actually we don't have a great answer to that question. This question has been answered very convincingly for mountain glaciers, and that's because for mountain glaciers, it is generally the case that, like in other climate attribution contexts, the amount of change or ice loss in mountain glaciers is generally proportional to the amount of forcing, right? So more degrees of temperature change due to climate change mean, some proportional, amount of retreat or ice loss at a mountain glacier. That's not the case necessarily with moraine terminating glaciers, and that's because they have this sort of threshold response that I've already described. They can not change very much for a number of degrees of warming, and then all of a sudden they could retreat a lot, right? And this leads to this problem that basically it is possible that glaciers with threshold responses can retreat just due to random variability within the climate system. And so this work, led by a former postdoc, John Christian, who's now just started a faculty position at the University of Oregon. On the left in this work, he showed a world in which there's climate variability. So this is just an idealized glacier model, and a world in which there's no climate change, but there's random climate variability. And you can see in that world, in 1,000 realizations of the future evolution of this glacier, in the vast majority of them, this glacier kind of just bounces around and doesn't retreat very much. But in a few cases, a non-zero number of cases, the glacier undergoes a pretty significant and catastrophic retreat. However, if you add in a trend in the forcing on top of that, you increase the probability of retreat. And so using this sort of framework, this starts to allow us the possibility of making attribution statements about glacier retreats in places like Greenland and Antarctica, where we can say that the probability of retreat in these settings could be increased or multiplied by some amount due to climate change, human-caused climate change. And the really nice thing with the way that ice sheets work, which is that ice sheets are made up of many individual glaciers, is that ice sheets end up being natural ensembles of glaciers, which is very useful for the attribution problem. So an example of this is on the right, I'm showing observations from satellite of glacier retreat in Greenland between 2000 and 2010. So the places where you have red circles are places where a glacier has retreated, and the places where you have blue circles are places where the glacier has advanced. And as you can see, in the vast majority of cases, glaciers have retreated in Greenland. It's probably not a surprise to you to hear, but what this modeling study that John led showed was that in large ensembles of glaciers with very different topographies and experiencing somewhat different climates, the probability that a large majority of them retreat increases as the trend in climate increases. And in the case where you have no trend in climate, that's this dot in the bottom left corner here, or a very small trend in climate, that's a small fraction of the internal variability in the climate system. It is very unlikely that you have more than a few or 10% of glaciers retreating over some few decade period. So what this is telling us is that it's very, very, very unlikely that strictly due to random chance, you could get a situation like what we've observed in Greenland on the right occurring in Greenland. Now, we have to do this for like the actual real case of Greenland glaciers, and that's what these sorts of large ensembles will allow us to do. So, stay tuned in the future, more realistic attribution studies are coming. The other interesting new results that came out of having now access to these stochastic models is that as soon as you turn on stochastic forcing in ice sheet models, as we did once we developed the model that could do this, what you see is that the models start to drift, and they actually start to drift quite a lot. So this is a new study which is currently in review in the cryosphere, where we take a somewhat realistic model of the Greenland ice sheet, and we just apply kind of a realistic level of stochastic variability in the ocean melting at the front of the glaciers in Greenland, and also surface mass balance, and some other processes in the ice sheet. And what we find is that as soon as you do that, the ice sheet starts to lose mass, or as soon as you apply ocean stochastic variability in ocean forcing, the ice sheet starts to lose mass. And what we argue in this paper is that for the most part, the reason why this is occurring is, well, it's due to two reasons. One is that many stochastic processes or many processes in the ice sheet system are highly nonlinear. And when you put a nonlinearity on top of a noise forcing term, even if that noise forcing term is symmetric or Gaussian, it will produce an asymmetric response. That is to say, the mean will be non-zero of the noise term. So that is one thing that is causing drift in the system. But the other thing that's causing drift in the system is this capacity for instability. So basically, if you have the possibility that the system can be driven over a threshold of instability, what this will lead to is just randomly driving glaciers over the instability threshold. And so in Greenland, what this amounts to is the amount of drift that you get in this sort of realistic simulation in Greenland is equivalent to just nearly tripling the rate of ice loss at the edge of the ice sheet everywhere in the ice sheet, right? So this is like not a small drift term. This is quite a consequential drift term. And it's something that, because most ice sheet models are not stochastic, we're really not accounting for right now in our ice sheet model simulations. Okay, so that wraps up part one. That's by far the longest part. So I know, that I'm getting along in the hour here. I'm going to do two shorter parts here, which is going to get more now into some of the specific processes that occur in the fast-changing glaciers at the edges of the marine ice sheets. And so this is kind of our canonical picture of what a marine terminating glacier looks like and how it could change under, let's say, increased melt from the atmosphere or the ocean. Right. So in this picture on the left, in this cartoon on the left, you have a glacier flowing down from the top. And then when the glacier starts to go afloat, you have this floating ice shelf. I kind of showed a different side-on schematic of this sort of situation before. But that floating ice, because it is rubbing against confining land or slower flowing ice at the edges, there's friction being exerted on it. And so it exerts a buttressing force back on the grounded ice upstream, right? And so at the edge of this ice shelf, there's relatively little mass loss due to calving from the floating part of the ice shelf. So if we start to melt, the thing that makes ice shelves, these floating ice shelves, much more vulnerable to climate change is that they are in contact, well, they are generally thinner than the grounded ice, and they are in contact both with the atmosphere and the ocean. So two different reservoirs of heat in the climate system that can potentially melt them and reduce the amount of pressure that they're exerting back on the grounded ice. So if we get to a situation where the ice shelf has been removed due to melting from the ocean or the atmosphere, what we would call ice shelf collapse in our field, then this buttressing pressure is removed and the grounded ice that's flowing towards the ocean is going to flow faster and lose much more mass through calving or iceberg fracture and calving. And so this idea that ice shelf collapse could occur is sort of one of these switches which can determine how much sea level rise you can get from the ice sheet. And this has been observed in some places. I'll show an example here in a second. But yeah, this is the reason why this ice shelf collapse, it's sort of the key which unlocks faster rates of ice sheet loss. So on the left here, I'm showing, this is a great paper by Stein and Son from a few years ago, where they're looking at many different ice sheet models. So each line in this plot on the left is a different ice sheet model. You can think of, well, this is an intercomparison project. it's a different ice sheet model, which represent ice sheet physics in different ways, use different numerical methods, this sort of thing. These are simulations of the Antarctic ice sheet over 500 years after the present. And so in the figure on the left, you can kind of see the state of the art of intermodel uncertainty, which is these are control simulations. There's really no change in climate from the present. And you can see there's some spread on either side. Some models gain mass that's actually in the negative direction here, a little bit counterintuitively. Some models lose mass that's in the positive direction and contribute to sea level rise, even under a sort of control simulation. On the right is what happens if you just instantaneously remove all ice shelves around Antarctica. And you can see now that all models are in agreement that this will massively contribute to future sea level rise. I mean, the amount by which and the speed at which that occurs is, highly variable between models. But basically, there's general agreement within glaciology that if you remove ice shelves, you are going to produce a lot more sea level rise than you would otherwise. I mean, this is many meters in this case, if you look at the y-axis of difference between these. So understanding ice sheet collapse is very important for projecting sea level rise. And so this is the sort of also the other canonical reason why we study this problem. This is a very famous set of satellite images from the Antarctic Peninsula from the early 2000s. And this is the former Larsen B ice shelf. So you can see here, this is a satellite image from January 31st in 2002. You can see the ice shelf area. This is floating ice here. The glacier is flowing from the left into this floating ice shelf. And then this was a particularly warm summer in the Antarctic Peninsula. And so melt ponds start to form on the surface of the floating ice, right? That's the little blue speckles here. Apologies for the resolution. That is due to the satellite sensor, not due to your screen. But yeah, lakes start to form on the surface of the ice shelf. So 5 weeks later, here's what the ice shelf looks like. So to give you a sense, I have no scale bar here, but if you've ever heard the analogy of a Rhode Island size floating ice shelf or Wales size floating ice shelf disintegrating, this is the ice shelf that is being referred to. So this is a very famous pair of satellite images that showed that within about 5 weeks, you have this ice shelf, the size of Rhode Island, the area of Rhode Island, disintegrating into, thousands of icebergs, nearly, overnight. And so what could cause an ice shelf to disintegrate so quickly? And this has been the product of a lot of research in the last 2 decades. The question that I'm trying to answer here with this next part is rapid sort of month scale ice shelf collapse an expected product of climate change, right? And that's because whether an ice shelf disintegrates in a month or 10 or 20 years is important to determining the subsequent response of the glaciers flowing into it. If it collapses or it goes away over a longer time period, this gives a longer time for the glaciers flowing into it to respond. And generally speaking, we think that that means less contribution to sea level rise if the ice shelf disintegration unfolds over a longer time period. So what I'm doing in this next part is I'm drawing inspiration from percolation theory. So, you've taken a statistical mechanics course, you've maybe seen animations like this. This is the classic 2D icing model. This is the quenched form of that. So basically, this is a model where we have sites on a lattice, and we can randomly change those sites to be one of 2 states. And if the state of a site agrees with the states around it, you are at a lower energy. And so the system naturally wants to go towards the lowest energy possible state. It wants to minimize its energetic state such that you have these clusters or this organization within the system, right? So you're in this GIF, you're going from an initially random ordering of sites, pluses and minuses going randomly in different directions, to a situation where you have, organization within the system. And this is very similar to how water arranges itself on a surface. And so in this model, that I published in collaboration with Alison Banwell in GRL in 2019. We think of melt ponds on the surface of a floating ice shelf as being randomly located sites on a 2D surface. Well, actually, so in this example that I'm going to show in the next slide, it's on a regular lattice, but you can do it randomly as well, and then we do it randomly in paper. But you have these sites on an ice shelf, and on these sites, we randomly add water at different locations on the ice shelf. When the water reaches a certain threshold, all the water drains. And when you rapidly drain water from an ice shelf, you basically get this instantaneous elastic response of the ice, which can cause it to fracture, right? So you slowly put a load on an elastic plate, and then you instantaneously remove that load, and that can cause a fracturing response. And that's because ice is a viscoelastic material that, when stressed enough, can also exhibit brittle fracture behavior. And so in this model, and if you are familiar with sand pile models, this is going to sound very familiar to you because this is a form of a sand pile model. So in this model, when the lake drains, it fractures some area, some prescribed area around it, and it reduces the threshold for nearby ponds to also break. Right. So essentially what we are modeling here is the filling up of ponds on an ice shelf and then breaking and fracturing the area around them, causing the area around them to have a lower capacity until it reaches a threshold for fracture as well. So in this model, in this cartoon of this model, right, this melt pond reaches its threshold, it fractures, it lowers the threshold of a nearby pond. When it lowers the threshold of that nearby pond, that pond is now at its own threshold, and then it fractures, and it leads to lower thresholds for other nearby ponds. So you can see that you can get these, what in the sand pile modeling community are called avalanches, and what we call in this paper hydrofracture cascades, that can lead to large amounts of fracture over a large area in a short period of time. Generally, the sort of two time scales in this sort of model are the slow time scale of filling up of water in different ponds over a time scale of kind of weeks to months, and then the fast fracture time scale of ice, which is seconds to minutes. Okay, so here is an animation taking up your whole slide of what this model looks like when you run it. So each circle here is a different pond on the lattice. So again, I said this is an example with a regular lattice. The darker the color, the more water there is, or the deeper the water is in that site. And then when it reaches a certain threshold, it fractures, and you can see that you can get these cascading fracture events or hydrofracture cascades that extend over a large area, right? And so the black areas are places that are fractured on the ice shelf. And so slowly over time, as we randomly add water to more places on the ice shelf, you will move from a pristine ice state to a fractured ice state. And this is what that looks like. So the blue line here is the mean depth of water ponding on the surface of this lattice, and the red dashed line is the mean strength of ice on this lattice. And so as you add more water, you reach a point where you actually have a maximum of water. And as you fracture in more places and that water drains to the ocean, the mean ice strength of the whole ice shelf decreases. But the point of this plot, to show you of this plot, is that the decrease in ice strength is smooth, right? It's not instantaneous. You don't fracture the whole ice shelf at once. And in fact, you can look over a wide range of parameters of like the density of ponds on the ice shelf or the rate at which a hydrofracture event causes damage to the ice shelf. And what we find is that in general, there is a speed limit on how fast ice shelf collapse can occur, that under realistic densities of water ponding and hydrofracture damage rates, well, I mean, really for any hydrofracture damage rate, you can't get a cascade which spans an entire ice shelf in arbitrarily little time. And so what this tells us is that events like the Larsen B collapse in 2002 in the Antarctic Peninsula were probably scenarios not where the dynamics of fracture were causing very rapid disintegration of the ice shelf, but rather it was an abnormal year. And we actually know this from climate records, that was a very abnormal year where the amount of water that was being put onto the ice shelf was about 4 times more than any previous melt season on record. So instead of the rate of damage or the rate of disintegration of the ice shelf being driven by the dynamics of ice fracture, it was actually being driven by the sort of climatological factors that were driving. And so that's actually a whole another interesting story. There's been a lot of work done on atmospheric rivers in Antarctica. These are storm events that bring warm air and precipitation to the Antarctic ice sheet. I'm not going to talk about that here, but it has led to a lot of interesting work in the last 5 years. Okay, all right. I'm going to kind of try to move things along here. Last little bit. So the picture that I have drawn, the simple picture that I've drawn of melt ponds on the surface of a floating ice shelf is very simplistic. And here's what melt. Oh, sorry for the volume. Here is what melt on the surface of an ice shelf looks like in reality. So this is a video from a Korean polar research helicopter from a number of years ago, looking at the Nansen ice shelf in Antarctica. And what you can see here is that the melt on the surface of this ice shelf, that waterfall, those waterfalls there, that's like a few hundred feet tall. So to give you a sense of the scale here. The water that is ponded on the surface of this ice shelf is not arranged into lots of small, well, it is arranged into some small isolated lakes, but it's also eventually organizes itself into these rivers. And so we need to start to understand not just how water ponds in one location, but also how it flows horizontally over the surface of the ice sheet. And so we have this grant from NASA to do just this. And so a former postdoc of mine, Sammy Buzzard, who is now an assistant professor at Northumbria in the UK, she is building this Python native 3D model of water flow over and down through snow over floating ice shelves. And you can see, so this is an example on the left of what happens when you start to randomly put water and let it flow on realistic ice sheet surfaces. So this is based on a digital elevation model of an ice shelf in Antarctica. You can see that it starts to arrange itself into rivers in addition to these sort of isolated melt ponds. So this water flow is actually quite important in reality, and we would like to include the effect of these melt ponds in a way. So this kind of model is very useful. It's very computationally expensive to run this sort of thing. And this is, in this example here on the left, this is like 100-meter resolution. So very, very high resolution compared to a climate model or something like that. So Danielle Grau, who's a grad student in my group, has been using some ideas from mean field theory or mean field theory for percolation models to develop a parameterization of melt pond depth and area on correlated random surfaces, right? So there's a number of papers in physics about basically how percolation and clusters develop on random surfaces, but largely typically those mean field theories have not been extended to correlated surfaces, which are Earth surfaces are correlated surfaces, ice shelf surfaces are correlated surfaces. And largely why they haven't been extended to long-range correlations is because you cannot write down a mean field theory by hand. And so in the physics literature, they haven't gone that far. And so what we did is we started where they left off, and then we used Monte Carlo simulations to basically explore the part of parameter space that is realistic for ice shelves and other Earth surfaces where you have long-range correlations of the surface topography of the ice sheet. And so what this allowed Danielle to do was to develop a simple equation which parameterizes. So an example here is on the left. A numerical model shows the lake depth under different kinds of roughness characteristics for the ice surface and different amounts of water supply. And what is the mean depth of lakes, melt lakes that you would get in that circumstance? And then in the bottom is a parameterization, right? A single equation that would be obviously very simple computationally to use within an ice sheet or climate model. And then on the right is the sort of gold standard, comparing it to observations of actual melt pond lake depths. So this is at the Amory ice shelf in Antarctica, and here the black dots are observations of melt pond depths over a few years, and the green shading is predictions from the parameterization. And showing generally that the parameterization is doing an okay job of reproducing observations. So the next step for Danielle is to incorporate these parameterizations and ideas into NASA's large-scale climate model to understand the effect of the albedo change from these superglacial melt ponds within the climate system, and then eventually to incorporate it within an ice sheet model as well. Okay, last part. I can see that I'm basically out of time, so I will just skip to the end. If you're interested in granular physics, you've seen nice simulations like this before. So this is work we did a number of years ago using a very computationally expensive model to simulate icebergs packed tightly together and being pushed by a glacier. And what we found was that basically the icebergs pushed back on the glacier and made it less likely that the glacier would produce more icebergs. The problem with these models also is that they're very computationally expensive and cannot be run on long timescales. And so new work funded by NSF with a fun cast of collaborators is using ideas from granular physics, particularly non-local granular fluidity rheologies, to develop continuum models for this granular iceberg flow. And so those are meant then to be incorporated into ice sheet models in the future. All right, I will, since I'm out of time, leave my takeaways up here, and I am happy to answer any questions that you have. And if you want to reach out to me about anything that I've talked about here today, my contact info is on the bottom right.
All right, thank you, Alex. Beautiful talk.
Thanks.
We have time for questions. So you can simply raise your hand or put questions in Q&A. And while people are thinking about their questions, maybe I'll start with my question, Alex. So I was wondering for the first part, you showed that the ensemble simulations show ensemble spread increase exponentially with time, and then it's skewed towards higher sea level rise prediction. So are these conclusions true when you start to incorporate different mechanisms in the realistic ice sheet models, such as cupping, and there are several other mechanisms that you include?
So yes, and that's I kind of showed a few examples of ensembles from real climate models, right? So these are like real, very realistic, state-of-the-art climate models or ice sheet models. And it is true while you are going through this sort of rapid, unstable retreat of glaciers in the ice sheet. Once those glaciers have finished retreating in at least the mean of the ensemble, then actually the distribution of projections starts to narrow again, and the skewness goes away. So it's not true forever, but on the timescales that we're practically interested in of decades to centuries, it is by and large true that uncertainty increases.
Cool. And Olivia, you have a question?
So I have a quick question for the melange work.
Okay.
I have went through Alex's paper on the continuum theory very carefully, and I'm just curious, the JGR1. So I'm just curious, because for the buttressing force, you basically have the compulsion from thickness, the glaciostatic pressure, and you also are influenced by the rheology of the melange, extensional flow or compressional flow. So how do you expect, in reality, how much proportion these two components contributes to the real buttressing force?
Yes, so I mean, it's definitely true that the buttressing force goes like the thickness of the melange at the terminus. That is something that is consistently true. And then in terms of the rheology, we definitely find that it matters, and it's largely because the rheology, basically the parameters that go into the granular fluidity rheology determine the shape of the melange, right? So as you know, the longer the melange is, the narrower it is, and the thicker it is, the more buttressing force it contributes. And the width obviously is just going to be set by the fjord geometry, but the thickness at the terminus and the overall length of the melange are largely determined by the different parameters. And so this is really where like experiments and DEM simulations and hopefully observations, although there's a question about how much you can use observations to constrain these things, but all of these different ground truths are very important to get these parameters right. Because like as in like ice shelf models, where the rate factor, the viscosity of ice determines how much buttressing the ice shelf does. We need ways to set these parameters in reality. And so those experiments and DEM simulations are going to be really important for setting the parameters in that rheology.
It's very exciting. We can have an accurate boundary condition for ice sheet models.
Yes, that's the goal.
More questions for Alex? Maybe I have another quick one. So for the second part where you use this melt pump model for to estimate the timescale of ice shelf collapse, are you aware of a strategy to incorporate this into an actual ice sheet model? Because this seems to be a big missing component. Like people haven't been able to incorporate this idea of timescale of ice shelf collapse into a realistic ice sheet model.
Yeah, I think that's really where, Sammy and Danny's work is going. I think on individual glacier simulations, the goal is ultimately that Sammy's high fidelity model for surface hydrology will be incorporated into those models. Now, it then has to be coupled to some sort of fracture parameterization, right? And that's obviously still an area of, uncertainty and development, research development and all of that. But you can envision, and this is exactly what Danielle will be doing for the last chapter for PhD, is you can envision an ice sheet model where you have something like a nigh zero stress model for fracture propagation in the ice shelf, that the parameterization, like this parameterization right here, it makes a prediction for lake depth, right? And then the lake depth goes into your fracture parameterization, and it is used to determine how far fractures have propagated. And if the fractures propagate through the full thickness of the ice shelf, then you might say, okay, then a calving event occurs or something like that. And so that is the plan here, is that this will be actually put into ISSM, where it will be coupled to the fracture parameterizations in that model.
It's pretty cool.
Yeah.
Okay, so we're like 5 minutes past 10 a.m. But that's all. Thank Alex again for a wonderful talk. And I will just remind everyone that the next seminar will take place February 14th. Professor Ralph Ferrari from MIT will talk about ocean dynamics. And this talk will also be made available on YouTube, and hope to see everyone in a month. Thanks, Alex, again.
Thanks, Yao. Thanks, everyone.
Thanks, Alex.